We started section 10.3 last time, and we had left off talking about scatter plots. And we had created this lovely scatter plot right, where'd it go? It was up at the end, that's right, right here. And we talked about the fact that your problems won't really start and end quite like this. They'll be much more simplified in creating the scatter plots, but the scatter plots that you have, that you will be creating trend lines through, will look a lot like this when you get them. So you'll get a bunch of collection of dots. And we even talked about sort of a general idea of what a trend line is. We're trying to balance the dots with a line that goes in the direction that the dots are sort of moving as you go from left to right. So in reality, a trend line, by definition, is a line that closely fits the data and can be used to describe it. It is also sometimes called a line of best fit, or a best fit line. Now, we were very detailed and specific in how we created our original graph, and I told you I'd talk to you about the exact reason why, so we're about to do that. We made sure that we really started at a specific value. We started at the year 2000, that we were careful that we broke the graph vertically so that we didn't think that we were hitting the axis and hitting zero, those kinds of things. So as we take a look at this, the line that I create will probably not be exactly the line that you create. So get out a straight edge of some sort. If you need a straight edge from me, I have some as well. Let me bring some rulers around. So rulers, protractors, your ID card. That's a good straight edge sometimes, or your phone case. But if you want a ruler, I've got them. So, you know what we do? You want one? All right. So you have the benefit of a ruler. I don't exactly have that, but I have the benefit of lines that draw straight automatically. So it's kind of the same thing. And so we're going to draw our data so that it fits the general direction that the graph is moving, right? And it looks like it kind of balances the number of dots below and the number of dots above. That's kind of our goal as we create this line. For example, well, let's not do that. Make it solid. And thinner. That's hard to see. A little too thin there. Okay. For example, this line looks like it's going in the general direction, but it's not balancing the dots very well, right? However, again, this is one of those benefits of technology that I have that you don't. If I shift it just a little bit, that looks pretty good. Okay, so you're going to try and use your ruler to balance the dots that are going across your line, okay? And if your line doesn't perfectly match up with mine, that's totally fine. Remember, I had grids as well. You do not have a grid. At least most of you probably don't. Okay, did we get a line drawn? Lovely. Okay, so what we're doing in example number 3, I actually didn't show that screen, but it's on your notes, is that we're using the data to create the best fit line. We did that, so we've done part A. It's the picture that we just drew, right? Part B is an equation for the picture, okay? This is the reason why we were so specific about what we did in making our axis what we made it, is because a line has a general equation, at least one of them, the one that we're going to use, is y equal mx plus b. Shake your head if that looks familiar. Good. So the b is where it crosses the y-axis. So by being very careful, or at least attempting to be very careful, we were able to see that our y-axis right here is the year 2000, right? That's our starting year. And mine's crossing it, it's almost 58, so I'm going to call it 58. So yours is probably somewhere between 57 and 59, let's say. Does that sound about right, where your graph is crossing? Somewhere in that area? Okay, so your equation needs to match your graph. I'm going to write it on the screen and not keep flipping back and forth, and then I'll copy it over there when I'm done. So it's y equals, I'm skipping over the mx part for a moment, and I'm going to put my y-intercept. My y-intercept looks like it's at about 58. I'll even write it more specific. I'll call it 58 and a half for, just for funs. Looks like 58 and a half on mine. What does m represent in an equation? Do you remember? Slope. Slope is the steepness, right? So as I'm looking at the slope, if I have grids, it's kind of nice because you can probably count it. If not, then finding locations where it looks like you're hitting corner points is good. So what do I mean by corner points? Well, on a grid, you can see the corner points for what they are. But on your graph, if you do not have a grid, you're looking for places where it looks like maybe you hit one of your dots exactly. Like mine looks like it hits really nicely at the year 2020 or 2002 and 62. That's where mine looks like it hits really nicely. And then I would look for another place where it hits really nicely. And mine actually looks like in 2003, it actually hits really nicely at 64. So I could count that on my screen. How many did I go up? How many did I go over? I went up 2 and went over to 1, and it's pretty straightforward. But if you don't have a grid, or if it doesn't end up being that close together that counting is really just clean and easy, you could actually do it with an equation as well. So let me use the ones that are looking like on my screen. Mine look like these two. So this one right here was the year 2002 and 62. And this one is the year 2003 and 63. 64. So sorry, 64. There we go. So whatever yours are that looks like those sort of corner points, use those. Don't use mine if yours doesn't quite match up with mine. Use yours. And then the way that we find slope is we do the change in y. That delta means change in over the change in x. Or you might have memorized it as y2 minus y1 over m, not m, goodness, x2 minus x1. And you're going to take one of those ordered pairs. So I'm just going to take the later one, that's the 64. My 64 is my y value. My x value is the 2003. And then the other point that I had was a 62. And the x value was 2002. So whatever yours are, you've got the inches on top, or centimeters, what was it? Centimeters on top, and you've got the years on bottom. And if I do the subtraction and division, it's 2 over 1, or it's the number 2. So yours may not be exactly 2, and that would be okay. But it's not going to be like crazy different, right? It's going to be close to 2. If you've gotten something that's like 1/2, that's not close to 2. There's a mistake somewhere. We need to check on it. Maybe you flipped your fraction upside down, right? Or maybe you misread your graph. Okay, so there's things that can come up that make things wrong, but there's also lots of things that could make it right. So in my equation above, this would be 2x plus 58.5. It is not complete. I want you to write this in bold, highlight, circle, underline, draw attention, star, whatever it takes. You must include units. So what does that mean? Well, it means that the x and the y here have no meaning right now. If I asked you, well, what's the vertical jump heights in 2012? Well, you wouldn't know what 2012 is for x and y. Is it x? Is it y? Do I put in 2012 for x? Right? What do I do with 2012 if I want to know what's happening in 2012? Well, you have to actually write those details in to give information, right? It's like the key to the equation. What's the key? Like kind of like when we did titles and all the graphs. Like, what's the key? So what you do is you can actually just write this down. X is this and y is this. Okay? So on ours, x, that's this horizontal axis at the bottom, it tells you, we labeled it this way on purpose. It's the number of years after 2000. So that information alone tells us what we put in for 2012. Oh, it's 12. Because 2012 is 12 years after 2000. Now I know the number 12 will go in for x. I still have to label what y is because I need to know what I've received out of the equation. I'm going to get a number back. What does that number mean? Well, y is the jump height in centimeters, right? It's exactly what I wrote down on my y-axis. All right, they come from your graph. It's not like something you have to create from scratch. But they can only come from your graph if you've been careful in how you've created your graph. Now, did we have to start at the year 2000 here? No, we did not. We could have started at the year, say, 2022. Like our first data point was 2002. We could have made that our y-axis. The tricky thing about that is that it makes this a really awkward way to describe it, right? So the year 2012, what I put in? Well, now I put in 10, because 10 is the number of years after 2002. So my general rule of thumb personally is that I try to make the vertical axis, the y-axis, a year that's a nice starting spot, right, with a tens digit or ones digit of 0, right? It starts in 1990, it starts in 2000, it starts in 2020, whatever. I don't want to start it in 2024. That's going to be weird, right? The data just looks awkward and strange when I write it that way. But if I started this one in 2000, it worked really nicely. Does that make sense? Okay, so this is my equation and all the work. I'll copy all of it that I would be doing for part B. That fits in pretty nicely there. This note at the bottom. This must contain appropriate supporting language. That's the units that's talking about. This appropriate supporting language is this telling what x equals and the y equals. What are they? In order to allow the equation to have meaning. Without that, the equation means nothing. It cannot be used to do anything, and that's the whole point of creating it, is to use it for something. So we're going to do that. Using your equation, what would you predict the jumping height would be this year? Well, what is this year? 2023. So 2023 would mean that we're using x equal what? 23. So we're going to do y equals 2 times 23 plus minus 58.5. And if you have a different slope value and you have a different y-intercept value, it's fine. Just use what you have. Don't use what I have. Use what you have. And then we're going to calculate it. So 2 times 23 plus my 58.5. Yikes, these are going to be some tall folks. Long legs. I have 104.5 what? Centimeters. Yeah, centimeters. Now, is it realistic? Well, probably not. In part because we've gone really far outside of the range of values that we were looking at. If we had predicted 2011 or 2012, that might be a pretty good estimate because it's really close to my data values. The further out we predict, the less accurate our prediction usually ends up being. Does this make sense? This is always challenging when I ask questions on the test for students. So please ask if you're not connecting something here. Okay, we're all right for now?
Oh, wait, I have a question.
Yeah.
So you were saying the whole 12 years or 10 years. I don't understand where you're getting those two numbers.
I made them up.
Okay.
So I was saying if we were looking at my graph over here, if we were looking at my graph over here and I wanted to predict something in 2010, say, I would be looking at 10 years after 2000. So that's where the 10 would be coming from, is because 2010 is 10 after 2000. And I've let my y-axis be 2000. If I'd let my y-axis be 2002 and I wanted to predict for 2010, I'd only have 8. It'd only be 8 years after the 2002.
Gotcha.
So whatever you let your y-axis be, which determines your y-intercept, that's how you have to predict your values for and how you're using your x values later. Okay? Good question, Lauren. Thank you. Okay. I had that. Oh, okay. There's one more thing that we didn't write down last time because I was going to mention it right here. It's on this. Actually, it's on a screen I don't have it typed on there. Okay, it's at the top of your graph. It's not at the top of my graph. At the top of your graph, it says to predict, not predict, it just says what kind. What kind of association? Do you guys see this? Okay, good. What kind of association is there? So I mentioned this last time, but we didn't actually write it in, and now my graph is such a mess. Let's actually highlight it to draw attention to where we are. Okay, the type of association has to do with how the line is drawn. So we drew the line, that's how we make the decision. So we've drawn this line in, my line is in red, and the line is telling us that I have a slope that is, okay, the slope's not increasing, careful. The slope's positive, specifically it was the number 2. Okay, so the slope tells you the association. The slope is positive, so my association is positive. So the answer to this question, and you can just write it above your graph where yours piece is actually asking it to you, this is a positive association. Now I don't really have to draw the line to sort of know that, right? The line's going to be going uphill. But if I've got the line drawn, or if I'm looking at the equation itself, right? If I'm looking at this equation down here itself, I should be able to make the decision about what this association is. The association is positive because the slope, too, is positive. And always remember the slope is what's attached to x, not what's attached to the end with the addition. So knowing that piece of information, we're able to do the same thing with equations, which is where we'll end our lesson. We have 3 equations given to us, and we're asked to decide what kind of association we have. Okay, so I'm going to pause and let you write down what you believe for A, B, and C is the association that's there. After you've written your 3 words down, turn to a neighbor. Ask them what they got. Okay, what do we get on the first one? Negative. I agree with you. It is negative. What we're looking at is the slope, and the slope here is a -2. How about the next one? Positive. Also agree with you. It is a positive association because my slope is 4. What do we get on C? It's 0. So the slope is 0. Okay, so kind of make a note to the side. This doesn't answer the question directly yet, but the slope is 0. Now, it's not really written in that way, but can you imagine this being written as 0x plus 8? Yeah, so the slope is 0. What we actually say when we have the slope being 0 like this is that there is no association, or the association is that there is none. And if you imagine having the graph, a 0 slope means you have a horizontal line. It's flat. So there is no association, right? As it increases, it never changes. So there's no association based on that. All right.